So today we'll be doing scanning. Last time we started introducing scanning, and we reviewed, basically most of last lecture was spent on reviewing the concepts of a DFA, NFA, and a regular expression. Deterministic finite automaton, non-deterministic finite automaton, and regular expressions. And we will be using this to build a scanner. And the scanner is that stage in the compiler in which we recognize words or tokens. So we don't recognize sentences. Sentences which correspond to statements. You know, this is the human language, and this is the programming language. So words correspond to tokens, and sentences correspond to statements, and recognizing words is the scanning, while recognizing sentences is the parsing, which is the part that we haven't gotten to yet. Okay. And last time we mentioned that to recognize words, we can use NFAs, DFAs, and regular expressions, because it's the language of all words, all valid words, in a typical programming language, okay, is a regular language. So it's a regular language that includes all the valid words in a typical programming language. And the words in a typical programming language are the numbers, you know, the integers, variable names, the different operators, and the keywords of the language. So these are the main parts of speech in a language. Numbers, constants, variable names, which we call identifiers, operators, the different operators, plus, minus, and the keywords of the language. Keywords like, you know, if, else, while. So the language of all, what we will be doing in scanning is that we will define a language for each one of these different parts of speech, and the language of all valid words is just going to be the union of all of them, right? So last time we started giving an example by looking into a regular expression for unsigned integers. So now when it comes to programming languages, our sigma is going to be the set of all symbols, all valid symbols in a programming language, in the programming language that we are designing a compiler for. So we'll have all the numbers, we will have all the alphabetic characters, A, B, through Z, and we will have even uppercase A, B, through. So this is little z, and this is big Z. And we have all the symbols that can appear in a valid program. Like, you know, plus, minus, equal, etc. Okay, so this is our sigma. So this is not the whole thing, but now you understand that it has all the symbols that you can type in when you are writing a program. This is our sigma. Now, given this sigma, we need a regular expression for an unsigned integer. So we need a regular expression for an unsigned integer. And the first attempt may be something like this. By the way, we will use a shorthand for for numbers and alphabetic characters. So for numbers, we will use the shorthand 0 to 9. We'll use this. 0 to 9, this means all the numbers from 0 to 9. And for alphanumeric, for alphabetic, sorry, we will use A to Z. So this is different from what they're using in the book. In the book, they're using ellipsis instead of the hyphen. And we are merging the we are merging little letters with capital letters. Okay? So this just means all of them, all alphabetic characters. Now, a regular expression for an unsigned integer, the first attempt is something like this. 0 through 9 star. And you can repeat as many times as you want. Okay. Now this is fine, but this will allow things that we may not want to allow. Like, for example, 0, 0, 0. So this will allow us to write 0, 0, 0. So, yeah. This will be an acceptable string that belongs to this language, right? So you can repeat. But to avoid this, to avoid leading zeros,
you would limit the first character.
Well, you can, yeah. So the first character has to be a non-zero. So you can do it like 1 to 9. But then what's the problem? Yeah, so you can add the 0 by itself. So you can just add it union 0. So you can do union 0. You either have a 0 or you have, 1 through 9. What I meant is 1 through 9, then followed by 0 through 9 star. So here I'm saying that the first, you either have a 0 or you have a non-zero followed by any combination of numbers. Okay. So this one, this allows leading zeros. This does not allow. By the way, in this course, our objective is not, knowing what should be allowed and what shouldn't be allowed. We are given the specifications of a language, and we are designing a compiler for that. So who decides, whether leading zeros are allowed or not allowed is the designer of the language. Someone writes the specs for a language, and based on the specs of this language, we build a compiler that implements these specs. Okay? So we tell you, whether leading zeros should be allowed or not, and we ask you to build a compiler that implements this. Okay. So now, this is an RA. Now for this RA, it will be easy to think of a non-deterministic finite automaton that is equivalent to this, right? For this is our start state. Then we have two possibilities, right? So we either start with 0, and if we start with 0, what will happen? We'll go to an accept state. And if we start with a non-zero, we'll go to another accept state. But what should we have in this accept state? A loop. So you can have anything that you want. You can have anything 0 to 9. So this is the equivalent NFA. So today we will be covering the Thompson construction, which is a systematic way of converting a regular expression to an NFA. But here we are doing it informally. We are doing it just by inspection because it's so obvious and intuitive to convert this regular expression into an NFA. By the way, this will also allow something bad. What will this allow?
Values too large to fit in an integer?
Well, okay, so this is definitely not setting any limit of the size of the integer. Okay, but you know, from a syntactic point of view, that may not be a big problem. What is the bad thing that is allowed here?
It allows an empty symbol.
Yeah, an empty symbol. So this will allow you to write something like x equals nothing. You know, so, right? But this is not what we want. So this allows the empty string as well. Allows empty string. So the empty, it's saying that the empty string is a valid unsigned integer, which is not true. It's a valid unsigned integer has to have at least one number in it. Okay. Now, how about floating point numbers? So floating point numbers. So this gives us an integer. So this is 0 or 19 followed by 09. So this gives us an integer because a floating point number can be an integer, but it can also have what? A decimal point. So let's say that the decimal point is optional here. Floating point numbers with an optional decimal point. Again, in this course, it's not our job, to decide whether it's, the decimal point is optional or not optional. This is given to us, and we build a compiler that satisfies these specs. So if the decimal point is optional, then how do we express this? So let's say that the decimal point is not optional. So we'll put a decimal point. Then after the decimal point, we'll have what? Yeah, we can have integer. Now, you may allow the empty, so you can simplify things and put 09 star. Now, if you put 09 star here, you are allowing an empty string after the decimal point, which could be fine, right? If you write something like x equals find point 5 point. Okay, this still at least this is meaningful. At least this has a meaning. So point nothing is like 0.0. So this allows you to have nothing, after the decimal point, or it allows you to put as many zeros as you want. So this will allow this. It will also allow but if you do it this way, this is a regular expression for the decimal point. But here, we're saying that the decimal point is what? Mandatory. So if we want to make it optional, what should we do? So if we want to make the decimal point optional,
You can wrap the whole thing. You can make the Like you can make the decimal point and everything after it, all of it optional.
How? So how do we express this using regular expressions? That's the question. Yes?
Parentheses, right? If you put parentheses before the decimal and after the star,
But that will have.
and then a star afterward.
Parentheses?
And put a
Like this?
No, you
So this makes it optional?
no, and
No,
then
you-
put 0 or 1 afterwards in the top right.
There's something in there.
you union that with the empty string.
Okay, yeah. That's exactly the solution. So if we union this with the empty string, so we can either have this or nothing. Okay, so we can have either this or nothing. So in this case, and okay, is this is what I have on the board, does it express what I want to say here? No, it doesn't. It's wrong. It's not expressing what I'm trying to say. So okay, so this doesn't do what we are trying to do, because this here, this is concatenation, right? Which has higher precedence, concatenation or union? Concatenation has higher precedence than union. So with this, so we're saying that this is concatenated with this. So this is not what we want. So we should use parentheses to force the order that we want. So in this case, we're trying to say that this is what we have, and this is concatenated with this or this, right? So we're saying that this whole thing, so this is the integer part, this is concatenated with the decimal point, and we can, the decimal point is the decimal point, and whatever comes after the decimal point is optional. Let's do variable names or identifiers. So for an identifier or a variable name, normally in a C language, in a C-like language like C, C++, or Java, we allow the variable name. What are the rules for a variable name in C, C++, and Java?
Must start with a letter,
Uh-huh.
and then after that you can have letters and numbers, and you can have an underscore.
And you can have an underscore. Yeah, exactly. So how do we express this using regular expressions? So with regular expressions, you have to start with a letter, right? So it's going to be A through Z. Then what?
A to Z, comma, 0 to 9,
Yeah.
comma, and
A to Z.
they
Then
won't be in the same bracket.
yeah, A to Z, or 0 to 9, or underscore. And this, we can repeat it as many times as we want. Okay? Well, in fact, yeah, in C and C, C++, you can start with an underscore too. So if you want to do this, you should do, okay,
You can, that's right.
underscore. But it doesn't matter. Again, we're not discussing, what should be allowed and what shouldn't. We're just implementing the specs that we are given. But here we are allowing an identifier to start with an underscore or a letter. Then after that, we can have as many letters, numbers, or underscores as we want. Yeah.
Are we okay with it ending with many underscores, just trailing?
I think it's allowed. I tried once.
It is.
I tried to define a variable as a single underscore, and it was accepted. So okay. So I tried once to do this integer integer underscore, and then I did underscore equals 5. Or, underscore equals underscore plus underscore. And this was accepted. So, and again, for here we're not discussing what should be accepted and what shouldn't, and whether this is good language design. So we're not designing the language. We're designing the compiler that implements a language that is specified for us. Someone specifies the language for us, and we build a compiler. But I have tried this myself, because 7 years ago a student asked me whether the underscore will be a valid identifier in C language.
GCC.
No, I think I tried it using the Microsoft compiler.
Oh, well,
But
there you go.
yeah. Okay. All right. So this allows. So the identifier starts with an underscore, then letters. Then you can have as many letters and numbers as you want. So with an NFA, the corresponding NFA here is. You will start with this, an underscore or A to Z. And then this is an accept state, right? And in this accept state, you have a loop with 0 or A to Z or 0 to 9 or underscore. So you can have these, you can loop here. Okay, so this is the corresponding NFA. Okay?
Well, one thing I want to point out, though, is that C and C++ do have a finite limit on the length of identifiers, and I believe it's 32 characters.
No.
Are
There's
you sure it's 32 characters? Well, in
And if you go beyond that, it won't distinguish beyond anything beyond the 32nd.
That depends on the linker.
okay, so now this raises an interesting question. Again, we are interested in the compiler design, not in the language design.
Right.
So we don't care what the language allows, but the question is, with this you can write an identifier name that is of an arbitrary length. So here we're not setting any length on the any limit on the length of an identifier. Now, how can we set a limit? So say if we want to set a limit of 5 characters. If we want to set a limit of 5 characters, then we don't have to. The star means infinity. Means there is no limit. You can repeat as many times as you want, right? So the star, what the star means is that you can repeat this as many times as you want. So it's unlimited. So you will definitely need something other than the star. And what's other than the star is you can just define how many numbers. You have a notation of defining how many times this can be repeated. So for 5 characters, you can say, okay, this is A to Z. Sorry. And then after this, you can have, well, let's call this whole thing, for convenience, let's call this thing X. Okay, just so that we don't repeat it. So if this is X, then we'll have either X or X repeated twice, or even X repeated 0 times, or so we can have epsilon. So epsilon or X repeated once, or X repeated twice, or X repeated 3 times, or X repeated 4 times. So this sets a limit of 5 characters, right? So the first character has to be a letter or underscore. what comes after this, you have up to 4 characters that can be anything out of this group. Okay, so this sets a limit, and it's tedious. You can set any limit you want that you want. So you can make it 10 or 20 or 30 or whatever. Okay. All right. Any questions on this? Yeah.
What do we have to check for dedicated words like if and while and
Have a union in front of it, or after it.
In fact, keywords, checking for keywords is trivial, because to write a regular expression for if, the regular expression is going to be if. This is a regular expression. So checking for keywords is trivial, because this is a valid regular expression because it has 2 symbols from the alphabet. And these 2 symbols from the alphabet, by the way, there is concatenation here. Usually we drop the concatenation symbol, which is this. Just like we drop the multiplication in algebra, we drop the concatenation in regular expressions. So this is I concatenated with F. By the way, what's a regular expression? A regular expression, in a regular expression, you can have a combination of the symbols of the alphabet, concatenation, union, or star. So these are the 3 operations that you can have in a regular expression: union, star, and concatenation, and any letters from any symbols from the alphabet. So recognizing a keyword is trivial. The regular expression for a keyword is the keyword itself. But the regular expression for the entire language is just the union of them. So a regular expression for the whole language is, regular expression for numbers, union, regular expression for identifiers, union, regular expression for operators, union, regular expression for keywords. Right? So it's just the union. An interesting construct that we would like to study a regular expression for is the string. Okay, so let's look at a regular expression for a string. So for a string, you may think that you may start with this. Then sigma star, Okay. So you can, this is your first attempt to write a regular expression for a string. But so this is, you're saying that you have the quotation, open quote, close quote, and inside of this you can have anything. Sigma star is just anything, right? But this anything, you want to exclude what? Closing, yeah, closing quote. So you can't have closing quote inside of this. So if you want to exclude it, so how can you exclude it? How can you exclude the closing quotes? You can exclude it by saying everything but, or the complement of, by allowing here the complement of closing quote. So you can say the complement using this, the complement of closing quote repeated as many times as you want, then closing quote. So what does this mean? The complement of closing quote, so this is everything or anything but closing quote, or this is equivalent to sigma minus the language of closing quote. Okay, so this is, by the way, and this complement operator, this is not a standard regular expression. So this is an extended regular expression. Strictly speaking, a regular expression cannot have this complement. So strictly speaking, a regular expression can only have union, concatenation, and star. But this is an extension. So this is an extension. We are extending the notation of regular expressions by allowing the complement, because this is convenient. Now, without this convenience, we will have to write all the symbols in the alphabet except this symbol. But this extension allowed us to write it much more easily and much more concisely.
I have a
Yeah.
question about that. That character you use, is that a caret or a?
Yeah, the caret. Yeah,
Okay.
yeah. Maybe it's not clear, but yeah, that's what I meant.